Okay, so let's finish this Cooper instability. So last time we calculated this denominator for this vortex function, which represents this Cooper, particle-particle channel diagram like this, and we mentioned that the denominator can vanish under two conditions. First, Q, the momentum transfer is very, very small, and temperature is actually very, very low. Okay? But today we will see that this temperature, when temperature approaches the critical temperature or the superconducting transition temperature Tc, and denominator vanishes. Okay, so let's just start from the last equation from the last lecture, where the denominator is given by this 1 plus this negative value of coupling constant lambda 0 times the density state at the Fermi level and times this integral over this energy in between this plus minus this Debye energy h bar omega d. Here this h bar can be said to be 1. And inside the integral, it is the hyperbolic tangent function of epsilon divided by 2 kBt and divided by this 2 epsilon. Okay, so let's just evaluate this integral. So you could define this dimensionless variable x, which is epsilon divided by 2 kBt, and you could convert this integral into this dimensionless integration over dx, and integrand becomes hyperbolic tangent of x divided by x, and there's a factor of 2 right here in the denominator, and the upper and lower bounds of the integration over x is rescaled by a factor of beta. Okay, so you could use integration by parts for this integral over x, and the boundary terms is this guy. It's the log of absolute value of x times hyperbolic tangent of x, and you take the difference between the upper bound value and the lower bound value and times the prefactor. And the remaining part of the integration is given by the log of the absolute value of x divided by the hyperbolic cosine square of x, which is simply just the derivative of the hyperbolic tangent of x. And there is a minus sign here, and you could evaluate this integral analytically. So this integral could be evaluated exactly in the low temperature limit, where this hyperbolic tangent function is almost 1. In the low temperature limits, remember that hyperbolic tangent runs from -1 to +1, right? And this is x. Okay, so when x goes to infinity, where its temperature approaching 0, or at least very, very small compared to the Debye energy, so this hyperbolic tangent, when x goes almost infinity, approaches 1. Okay, so this is the limit that we could take in the low temperature limit, and in that limit, this lower and upper bound of this integral over x becomes minus plus infinity. And because this is just a symmetric function with respect to x, so this is the factor of 2 times this integral over x from 0 to infinity of that function. And this function could be evaluated exactly analytically, and final result of this integral is given by this. It's a log function. Inside the log, there's a pi in the numerator, and in the denominator is the 4 times this e to the Euler constant, c. Okay? So you plug in this result, and also you plug in this upper and lower bound of this boundary term right here, And you can see very easily that the denominator, capital D, can be 0 when the rest of the term over here cancel exactly by this +1 right here. Suppose the remaining part of this integral and this boundary term sum up to be -1, and this denominator really vanishes. And this could be achieved. So if you use that condition, and you can see that the denominator vanishes when this integral plus this boundary term cancelled exactly by +1, which is this condition right here. And the log function right here is actually the positive valued number. And by the way, this temperature should become Tc, as I mentioned, which is a small but positive value. Okay, so at temperature approach Tc, and you could rearrange these terms so that this could be cancelled exactly by 1. And this is the condition that cancellation happens. Okay, so for attraction between electron and electrons mediated by electron-phonon coupling, whereas lambda 0 is actually minus value, take a minus value or negative value, and this condition is equivalent to this equation over here, which can be satisfied. Okay, and this sets this transition temperature for a superconducting state, Tc. You can invert that relation, and to get Tc, and this Tc is given by this number right here. This is a very famous value, 1.14 times the Debye energy times exponential function of -1 over this magnitude of lambda 0 times density states of electrons at Fermi's energy. And this value turned out to be in a good agreement with many ordinary metals near this transition temperature. And this BCS actually derives such a relation, okay? But maybe not, this by evaluating the Cooper instability, but anyway, they made the mean field approximation, and they were able to get this estimation of a Tc. And this is a so-called weak coupling theory, because this lambda 0 is really, really small, and density of states times this lambda 0 is also a small number. So you get e to the minus 1 over a small number, which is e to the minus very large number, and times the Debye energy. Okay, so but this is a very, very tiny number, exponential of -1 over lambda 0 times density of states. So, and if you multiply this Debye energy by a very, very tiny number, so you get very, very low transition temperature, Tc. So this typically this theory predict, say, the Tc to be somewhere around a few Kelvin. For example, 1 Kelvin, 5 Kelvin, so okay. So and this is so-called low Tc superconductors, and this is precisely what happened for ordinary metals, where this transition temperature to reach the superconducting state is really, really low, so single digit in Kelvin. Okay, but we see very clearly that this denominator vanishes, which means that this vortex function will diverge. As temperature approaches Tc. Okay, so this is what we call the Cooper instability. And of course, you can see that for temperature below Tc, this superconducting instability occurs, so that you expect that this kind of diagram will dominate the ground state. Okay, and then we will see that just a moment, that this Cooper pairs may form. So you can imagine that this effective electron-electron interaction in this particle-particle channel diverges, or the Cooper channel. As a result, a new ground state appears. And such a new ground state is what we call the BCS state. And which means that you could very easily imagine that these two electrons can actually form a Cooper pair. As mentioned last time, this Cooper pair is made of two electrons across the Fermi surface carrying almost opposite momentum and opposite spins, and they are coupled because of this Cooper instability. Okay, so now we finish this derivation of a Cooper instability, and so now we can officially write down the Hamiltonian of a BCS state, which consists of the kinetic energy of electron, conduction electron, and the effective attraction between electrons, okay, mediated by phonon, but we forget about all the other terms, and we should focus on this Cooper instability and trying to figure out this ground state and also the Green's functions, okay, a single particle Green's function. So in the Hamiltonian, we have the kind of a Coulomb-like term, two C daggers and another two C's, but we should notice that this is attraction rather than repulsion, okay? And immediately from this Cooper instability, we know that these two electrons must form a pair, and they must come together. They must be created or destroyed at the same time. As a result, we need to really think about this correlation, where you could simultaneously create two electrons or destroy two electrons and carrying opposite momentum and spin. Okay, and this is the origin of the BCS mean field theory, where they consider this kind of expression value below Tc. This expression value of this creation of two electrons across the Fermi surface carrying opposite momentum and spin, and this expression value remains finite. Okay, but this kind of electron-electron, say, pair kind of expression value being finite of this sort was absent in our previous discussions, and this is present only when two electrons are attractive to each other and they try to form a pair, Cooper pair. As a result, we need to compute this correlation function, okay? So, which says that you could consider that the probability that you could simultaneously create or destroy two electrons, okay, at the same time, say in this around the same spatial location or different spatial locations, and this correlation function does not vanish. Okay, and this is related to the Cooper pair wave function. So we know very well that this is a Fermi surface, and if you have two electrons across the Fermi level and they form a Cooper pair, and we know their momentum and their spin in K space, but what about the real space? Okay, so based on the uncertainty relations by Heisenberg principle, we are not sure their spatial locations are, because once we know exactly their momentums and we lose the accuracy in describing their real space coordinates. Okay, so we don't know where they are. we do know is that their momentum must be on the Fermi surface, and these two electrons carry exactly the same momentum and opposite spins. Other than that, in the real space, we don't know where they are. In other words, there may be a very long distance Cooper pair in real space, but they have this structure right here, and they sort of know each other, even though these two electrons are really, really far apart in real space. So the BCS ground state is nothing but the product of such Cooper pairs, wave functions. So you can imagine that the BCS superconducting vacuum, or the BCS ground state, is made of all the product of all these Cooper pair wave functions in real space or in momentum space. So we don't know where they are, but we do know they are Cooper pairs. Okay, so I guess that's enough for the introduction to this BCS state. So let's take a short break. When we come back, we will start to really perform some Green's function approach to this BCS state. Namely, we should formulate and derive the gap equation, which involves the pairing energy of this, which is proportional to this expression value of this quantity right here, and we should be able to evaluate this BCS gap from the Green's function approach. Of course, you don't need to follow this Green's function approach to get a gap. You could obtain this gap simply by this BCS mean field theory. Okay, but for further calculations, such as say this electrical conductivity, okay, so we should follow this Cooper formula, and Cooper formula is kind of a current correlation function. Okay, so when we calculate the current correlation function, we need to know the Green's function, okay, of each individual single electrons, but we know that each individual single electrons pair up with the other partner across the Fermi surface, and they form Cooper pair. So how do we describe the single particle Green's function? Okay, so in other words, when we really evaluate this current and conductance and spin susceptibility and so on in the BCS state, we must figure out this Green's function for a single electron. But that single electron is not free single electron anymore. It is paired up with another electron. Okay. In other words, we need to define two kinds of Green's functions. One is the particle Hall-like single particle Green's function. Another is exactly this kind of a pairing, a Cooper pairing, kind of a Green's function. Okay, so we need to formulate this so-called BCS gap equation, which link these two types of Green's functions. The first one is defined as G, and the second one is for off-diagonal Green's function. Okay, so both G and F involve in the BCS gap equation. Okay, so the following calculations are to figure out those G and F, and also the gap, the BCS gap. So for the gap, as I mentioned, this is very easy. You can simply just formulate BCS mean field theory and get a gap. You get a TC and so on. But to really calculate the G and F, the Green's function, are not so straightforward. Okay, once we are in the superconducting state and we like to study their transport property, for example, and this BCS mean field theory is no longer used for anymore. Okay, so we need to really build up this machinery to actually take advantage of this Green's function, both the diagonal and off-diagonal single particle Green's function in the BCS state, and then we could go on and perform any kind of calculations, and that could be measured in experiments Okay, great. So let's take a short break. So you can see this part of the lecture notes from in our textbooks, either Flansburg or Phantom Logica or any other quantum many-body textbook. So this Cooper instability calculation, also this BCS gap equation could be found everywhere. So it is a standard many-body theory. Okay, so let's formally start to introduce this BCS theory, especially we try to derive the BCS gap equation. Remember, this BCS gap is something related to this expansion value of the particle-particle creation, or the Cooper pair expansion value. And what we are doing here follows the Green's function approach, which will become very clear, all of you, that this is a very general approach. And once we know the Green's function, conventional normal single electron Green's function, also this off-diagonal Green's function, and we know everything. Okay, so the way that we derive such a Green's function in the superconducting state is by evaluating the equation motion for the Heisenberg fields psi r tau imaginary time domain. So this is the Heisenberg operator we have defined previously, which is related to the Schrödinger operator by this kind of a transformation. There's e to the k tau on the left and the e to the minus k tau on the right, whereas k is the Hamiltonian in our ground canonical ensemble, including this chemical potential, and also in the presence of a vector potential or magnetic field, and this psi dagger is defined in a similar way. Evaluate this Heisenberg equation motion for a single, say, destruction operator or creation operator psi dagger by taking the partial imaginary time derivatives psi, and by Heisenberg equation motion, this is given by the commutator between k or Hamiltonian and that operator. Remember that, all right? So, but our Hamiltonian or the operator k here shows the attraction between electrons, because this is minus g, where g is a positive constant, and times this kind of a two-body interaction strength. So we will evaluate this equation motion for a single Heisenberg field and also for the Green's function. So for the single equation motion for a single field, this is the Heisenberg equation motion, and we need to value the commutator. And this is the final results. You could check whether you agree with that. Okay, so you simply plug in this k and you apply this anti-commutation rules for fermion fields, and then you'll get this. So there are only three operators right here in the interaction term, and you get one field psi dagger missing in the kinetic energy term. And the reason why you get one operator out is because you already take advantage of this anti-commutation rules.
Excuse me, what is a Heisenberg field?
So this is the analog of our real-time Heisenberg operator. Remember this, if this is the real time, remember your quantum mechanics, standard quantum mechanics, okay? So suppose this is a real time. In the Heisenberg picture, the operator is related to the Schrödinger operator by this unitary transformation. Okay, so in the imaginary time representation of the fields, this is the analog of this Heisenberg operator.
Okay, so it's just different picture. I mean, the psi is squared for the fermion, right?
Right. This could be boson or fermion, whatever. In our case, this is fermion. And this is Schrödinger operator, and this is the Heisenberg operator. So let's just evaluate the equation motion for the ordinary single particle Green's function, G alpha beta. Ordinary single particle Green's function is made of this kind of a psi dagger with a time ordered, and you take the expression value of that. We could follow the same spirit when we derive the single field equation motion, and we could derive the equation motion for G alpha beta. Okay, so we can take the partial imaginary time derivative of G alpha beta, and then this will be given by this commutator of that G alpha beta and k, right? Okay, but what is the partial time derivative of g alpha beta, you simply just plug in this definition of the single particle Green's function over here, and you should distinguish whether tau is same as tau prime or different. Okay, for tau different from tau prime, you only take differentiation of the first operator, psi alpha, because this time here for the psi alpha is tau, which is the same as this tau. Okay, so but you also may hit this derivative of psi dagger beta, whether this tau is the same as tau prime, and so there's the second term right here. And inside this extraction value, this is any commutator between psi alpha and psi dagger beta. The reason why you have this is because we really like to interchange this to few operators to really take the differentiation, right? So when you take differentiation, you need really move this operator just to the next of this d by d tau. Okay, but what is the anti-commutator right here? This is nothing but delta function, right? Okay, delta alpha beta times this delta Dirac delta function, delta r minus r prime. So which means that when r is the same as r prime, you have contribution. If r is not the same as r prime, you have 0. Okay, same thing happens here. So this delta of tau minus tau prime refers to the fact that this only contributes if tau is the same as tau prime. So now you know what to do, right? Next, because we have this partial psi, partial tau right here already by equation motion for a single destruction operator, psi alpha. So, but let me just summarize this. So this is given by. Okay, so we need to go on to evaluate this thing, right? So the second term is nothing but delta function, bunch of delta function, but the problem is the first term right here, which involves psi dagger beta and partial psi alpha, partial tau, where you could plug in what we have right here and plug in here and see what happens. Okay, so what you will see is that the single particle Green's function, the equation motion for the single particle Green's function, depends on two particle Green's functions. Okay, so let me just plug in what we have. Okay, so when you plug in this, partial psi, partial tau, you get 1 psi alpha in the kinetic energy term, and 3 psi's in the potential energy term. But when you plug into this equation motion for g alpha beta, remember there's a psi dagger beta right here, additional psi dagger beta, which could be combined with this psi alpha here to form a Green's function. So that's why we have this g alpha beta here, because we could combine this psi alpha and psi dagger beta and to form another g alpha beta in the kinetic energy term. For the potential energy term, and this missing psi dagger beta is back, because remember we have the 3 operators after this equation motion psi alpha, but then we have this psi dagger beta, right? Another creation operator. Therefore, we are back to this 4 fermion term. Good. So let me just write it the full expression. So this is given by this delta function term and plus this kinetic energy term, which is single particle Green's function g alpha beta, and also the third term is the potential energy term, which is a 2 particle Green's function. This is a 2 particle Green's function. Remember, we can define a 2 particle Green's function, right? And when we evaluate this current correlation function, remember that the current correlator is nothing but 2 particle Green's function. And of course, the 2 particle Green's function could be decomposed in terms of product of the 2 single particle Green's function. So here we learn the lessons that the equation motion for a single particle Green's function depends on 2 particle Green's function. So a single particle Green's function depends 2 particle Green's function. So it's a bit messy. So to really solve the single particle Green's function, equation motion for this, we also need to solve the two particle Green's function. But how do we do that? Fortunately, we have the BCS approximation or mean field approximation, which allows us to decouple this two particle Green's function in terms of the particle hole channel and particle-particle channel. And this is precisely what I meant earlier, that we could decompose this in terms of some kind of a Cooper pair combination conjugate. This is a particle-particle channel, and we can also decompose this in terms of the particle hole channel. So in general, we have these two different types of approximation available because it is not easy or too complicated to solve two particle Green's function. So we could, based on our intuition and also the nature of the ground state, the Cooper pair in the ground state. So we could imagine that we have a finite expression value for this Cooper pair. And as a result, this four fermion terms could be decomposed in terms of a number which describes the Cooper pair strength times the operator, psi, or vice versa. But we could also decompose this in terms of particle hole channel, psi dagger psi, but this only renormalize the number of particles, because this is, remember, this is a number operator. You take the expression value of the number operator, you get the number. A number times psi dagger psi is nothing but the chemical potential term. So we could also do that, but this is easy to actually get away because we could redefine our chemical potential to absorb such a shift in the chemical potential when we perform such a particle hole mean field approximation. Okay, so in the following, we will consider only the particle-particle mean field, where in the BCS state or the BCS ground state, a Cooper pair is formed. In such case, this psi dagger, if you take a expression value in that state, in the BCS state, you get non-zero. And we simply just approximate this four fermion, so two particle Green's function, in terms of the classical number or C number times the operator, okay, quadratic operator psi, so that this four fermion term is reduced to a quadratic form, okay, times a constant commuting number or C number, okay. So the four fermion term is reduced to two fermion term. Of course, this two fermion term is unconventional because in a conventional, say, electron gas, you get C dagger C, but here this is a CC or a C dagger C dagger, so we need to diagonalize this mean field Hamiltonian, all right, okay? So let's take a short break. When we come back, we will start to decompose this four fermion term in this two particle Green's function in terms of a particle channel type of a mean field, approximation.
Before you give mean field approximation, the two particle Green's function will depend on the four particle Green's function. You can expand that to the infinity.
Yeah, you could say that, but then we need to make approximation anywhere, anyhow. Okay, you could go on, you could compute this equation motion two particle Green's function, and it involves four particle Green's function, and so on and so forth. Okay, or three particle Green's function. But in any case, this could go on forever. But we need to make progress. So without this mean field approximation, it is not possible to solve this complicated equation motion. Okay, so let's try to truncate this set of equation motion for G alpha beta by using this approximation that I mentioned, the mean field approximation. So basically what we do is to approximate this 4-point or two particle Green's functions by the product of the 2-point or single particle Green's function and a mean field or a gap. So and the more relevant approximation or decoupling of this four fermion term is the particle-particle channel that I mentioned earlier, that you could sort of approximate this four fermion product in the two particle Green's function in terms of a mean field, which I call this a gap or BCS gap, which is expression value of this psi dagger, and multiply by a single particle Green's function, psi 3 and psi 4. However, this single particle Green's function is not in the standard form, because in the standard single particle Green's function, it is psi dagger with the time ordered and expression value. Here is a two discussion operator, right? So it is a different kind of single particle Green's function, which we call this, say, off diagonal or anomalous Green's function, because this is not the standard single particle Green's function. This Green's function involves the destruction of two fields or two operators or two particles, or creation of two particles at the same time in this kind of definition. So, but again, we will derive the equation motion for F later, right? So now you can see that this is still not trivial, because we sort of make progress by approximation, mean field approximation, but then this mean field approximation brings us a new Green's function, which we didn't know what to do. So this Green's function is not there in the beginning, right? We haven't defined any kind of anomalous or off-diagonal Green's function before this. And this is the first time that we should deal with this unconventional Green's function. But this unconventional Green's function is tied to this gap, or BCS gap, or the Cooper pair strengths. And we should see later, when we really solve and derive this Ken omega representation of G and F in the BCS state, you'll see that both Green's functions are really non-trivial. And the second type of mean field is what we call the particle Hall kind of a decoupling, where we decouple this full fermion term in terms of the particle Hall mean field times this conventional single particle Green's function. But this, as I mentioned, could be shifted away, because this is nothing but some kind of a chemical potential, effective chemical potential times the C dagger C term. So this chemical potential term could be combined with the electron kinetic energy term, right? So this term could be absorbed into the definition of the chemical potential of a conduction electron. So therefore, we simply just shift the chemical potential, and we can ignore this term. So from now on, we should only focus on this particle-particle type of mean field approximation. Great, so let's just plug in this mean field approximation and see what happens. So we assume delta is non-zero. Okay, so now this equation motion for G alpha beta could be further simplified as this gap, the size of the BCS gap, multiplied by this off-diagonal or anomalous Green's function, F. All right, so G alpha beta is now linked to this F gamma. So we will formally define this F off-diagonal Green's function later, but let's just do this. Formally define this G up is the same as G down, because we have a spin kind of a up and down symmetry in this equation of motion. And so now we formally define this off-diagonal Green's function. This F is defined by this minus times this expression value of the time-ordered operator. Inside this bracket, this is the psi up, psi down, at different space and time location. So we can take the complex conjugate of that Green's function, and we define this as F dagger in a similar way. So we simply just take the, say, Hermitian conjugate of this F, that you get F dagger. So now you can see that this equation motion for G is related to the F. As a result, we need to really evaluate this equation motion for F, which involves G, right? So you can imagine that. So the equation motion for G is linked to equation motion for F and vice versa. So you get two coupled equation motion. And we need to simultaneously solve these two coupled single particle Green's functions. So let's just rewrite this equation motion for G in a simplified unit where H bar and C are considered to be a unit. So you get this. So this is the full version of the single particle equation motion for G up, which is related to this F dagger Green's function. So this is F dagger. And likewise, we could define the gap function, delta minus g. Okay, suppose this is our BCS gap function in real space, which is defined by this minus g times this Cooper pair expression value. So now you could use this definition of BCS gap to rewrite this gap function for g alpha beta. You get this. Okay, similarly, you could take the, say, Hermitian conjugate or complex conjugate of this equation, you get another counterpart, similar equation for f and g, but this time this right-hand side of the equation vanishes. Okay, so these two are very important equation motion that we need to solve. Next, we will try to make progress by solving for this kind of a coupled equation or motions. Okay, let's take a short break. Okay, so let's try to solve this coupled equation motions for G and F. So in particular, I just repeat what we have earlier previously. So this is the first equation motion for G and F dagger, but the second equation involves F. This is what not what we want. We want the equation motion for F dagger. As a result, we take the Hermitian conjugate, the second equation that I just wrote, and this becomes a third equation, or equation number 3, which is the equation motion for F dagger, which involves F dagger and G. So now we should solve this coupled equation for G and F dagger at the same time. And these two equations are called Gorkov equations for historical reason, maybe because it was first derived by Gorkov. So the solutions to these Gorkov equations come if we make a further approximation, which is some kind of a uniform medium approximation, namely this gap function, delta of r, is independent of position r, which is uniformly distributed. So imagine that these Cooper pairs could be formed here and there, but nobody says that this could be uniform or inhomogeneous, but we assume that this Cooper pair kind of a coupling strength is actually especially uniformly distributed. Of course, you could imagine this non-uniform gap Cooper pair distributions, but this is more complicated. So assume that this delta or delta star as function of r is just some number, which is independent position, and we could take a Fourier transform of the definition of the gap function. So remember, this is nothing but this f dagger Green's function, but in the limit of tau plus goes to tau, remember this is psi dagger, r and tau, right? This is the definition of a gap, right? Okay, times coupling constant g. But then, this kind of an equal time, same locations, kind of expression value is the same as f dagger correlation function, but you take the limit of tau prime goes to tau or tau plus. So, but we assume that this is simply just a uniform constant independent of r. So this f dagger in this real space, spatial and imaginary time axis could be evaluated by the Fourier transform in Matsubara frequency, which means that you could consider this is just a Fourier transformation of this f dagger r prime and omega n, where omega n refers to the Matsubara frequency, and you sum over Matsubara frequency of this e to the minus I omega n times tau minus tau plus. Remember, this tau plus is in the limit of the tau plus goes to tau, so tau minus tau plus is really, really tiny. This goes to 0. So in the limit of the tau plus goes to tau, this exponent simply vanishes, and so e to the some 0 exponents is simply just 1. So approximately this is given by this Matsubara sum of this f dagger function in this frequency domain divided by this beta times g. So this is simply just a gap function. You know that this gap function, it becomes very clear that it is nothing but average or sum over the Matsubara frequency of the f dagger Green's function. But what is f dagger? Well, f dagger could be solved by Fourier transformation of these two coupled equation motion. So let's just Fourier transform equation 1 and 3. Okay, so in doing so, we take the limit where r is not the same as r prime, so that this delta function really vanishes, okay, on the right-hand side. So you get 0 on the right-hand side. Here, Q0 refers to this, say, frequency, or Matsubarra frequency. So epsilon Q is a quadratic dispersion of the electron excitation energy, and Q0 is a fermion Matsubarra frequency. Okay, so you can easily solve this equation. Okay, so the solutions are the following. Okay, so the G in the Fourier space and Matsubarra frequency domain is given by and this is the solution for normal single particle Green's function G alpha beta in Fourier space. So the F dagger, for this capital E Q, is the Bogoliubov excitation spectrum for BCS state. So the BCS state is a state where you fill up all this negative branch of your excitation spectrum and leaving behind all the empty band of this upper dispersion, capital EQ, and there's a gap with the size 2 delta in between this upper and lower branches of this Bogoliubov band. So in the lower branch, all these electrons form Cooper pairs, near the Fermi surface. Now, of course, within the range of plus minus the Debye energy. And to get the excitations above the BCS ground state, you need to break the Cooper pair. You need to break the Cooper pair in order to have this excitation. So once you break the Cooper pair, you excite 2 free electrons, okay, in that empty band. And this is the BCS excitation. And so by solving the Green's function, G and F, we could find out what this Bogoliubov dispersion for the BCS state. But this Bogoliubov dispersion could be obtained by simply just diagonalizing this mean field Hamiltonian, 2x2 mean field Hamiltonian, the BCS Hamiltonian, which we have discussed in the previous semester. But I will briefly review this in the next lectures. Okay, so I guess that should be enough for today. We're almost there. So we figure out this Green's function, both the normal type and the unconventional off-diagonal type of single particle Green's function in the BCS state, which is rather different from ordinary free electrons, right? So in ordinary free electrons, you get what? You get this, right? Okay, so this is not that simple because form kind of Cooper pairs which affect the single particle Green's function. So now the single particle Green's function is not taking this simple form anymore, which involves the gap. But imagine this gap, delta, vanishes, then you could really cancel the numerator by the denominator, and you got exactly the same form here, right? So if delta is 0, so this is nothing but the square of that term, right? So you just cancel one piece of this, and you get this form, which means that this single particle Green's function G reduces to the free electron type of single particle Green's function if this BCS pairing vanishes. But more importantly, we derive this off-diagonal or unconventional type of single particle Green's function, which tells you, the Cooper pair kind of a strength. As a result, you can see very easily that this F dagger or F is proportional to delta, right? So if delta is 0, then F vanishes. So F directly measured how strong or how weak your Cooper pair. And so next time we will try to solve this gap equation, this BCS gap delta or delta star, which is taken as independent of R uniform value, which is nothing but this Matsubarra sum of the F dagger. But what is F dagger? We already derived this F dagger, right? Okay. As a result, we simply just plug in this F dagger back here, and we sum of Matsubarra frequency, and we get delta. But delta appears on both sides of the equation. On the left-hand side, you get delta. or delta star, but on the right hand side, this F dagger also involves delta. Right? So again, this is kind of a iterative gap equation, so-called BCS gap equation, and which we will study next time. Okay, so I guess that's enough for today. We're almost getting to the end of this BCS. Okay, so far any questions?
So the abnormal green function, there's no structure like kind of a lifetime, right? Because before the normal green function, there's 7 energy, and we can estimate the lifetime. But here it means.
Yeah, so which means that once the electrons are in the BCS states, they can live forever. You can see that how can you make them going away, right? Unless you inject the energy of the amount of 2 delta at least. If the temperature is low enough and you don't inject any external energy in your BCS state, and they will live there forever. Okay, so that's why we call them superconductors, because they superconduct. There is no energy dissipation. Yeah, of course, at finite temperature, there may be a little bit probability that you could break this Cooper pair, and you could have some small probability that you have excited state electrons, but you could almost ignore that as long as temperature is low enough. Yeah, okay, so we could discuss that next time when we talk about this correlation functions and electrical conductivity and so on. Okay, so have fun, and we will get to the end of the semester finally. So I expect that within 2 hours of lecture time, we will finish everything.